Next, we will have Xiaohua. Xiaohua Zhai is a staff researcher at Google Brain Zurich. Before that, he received his PhD degree in sales from Peking University and the bachelor degree from Nanjing University. His research interests includes representation learning, transfer learning, self-supervised learning, generative models, and cross-model perceptions. Xiaohua, please.
Okay, yeah, thanks for the invitation. I will present scaling vision and language learning with vision transformers. Just a little bit of background. So the visual task adaptation benchmark, it tries to train an upstream model and then adapt this model on arbitrary downstream tasks. So in this process, there are two parts. First part is upstream pre-training, where you get a large vision model on any upstream data set. And then for downstream, we hope this model can use an arbitrary adaptation algorithm that can solve very diverse downstream tasks. And the first part, like upstream pre-training, has been covered by Neil in the past talk. And in this talk, I will focus on how to adapt all of those pre-trained models to vision and language tasks. Let me start with LIT. It's called the zero-shot transfer with locked image and text tuning. The background is as following. With pre-training in the vision domain, normally one needs a pre-trained model and use this pre-trained model to fine-tune on different downstream tasks. Like if there comes task one, it has to do fine-tuning on task one, even though task one contains very few data, like one shot per class. On ImageNet is 1,000, but this still requires a very heavy engineering tuning process to make your model capable of the downstream task. And the second background is contrastive learning. In the recent years, using image and text pairs as pre-training data set, and try to align the embeddings from images and from text sentences in this embedding space is adopted by Clip and Align. And with this shared embedding across image and text, one can easily turn the classification problem to unseen domain by simply comparing an image and a target classes embeddings and try to rank the text candidates and choose the top ranked text candidate as a target class. Like ImageNet, you rank the 1,000 text labels. On background 3 is that even though this works pretty good on downstream unseen tasks, but however, we listed down some baselines like REST-50, which is the state-of-the-art methods quite a few years ago, and also the recent state-of-the-art with above 90% top-point accuracy on ImageNet. You can see that with zero-shot adaptation like Clip and Align, those methods actually is comparable with very old state-of-the-art, but there's a big gap between those zero-shot models and the recent state-of-the-art numbers on ImageNet. So with the locked image tuning, tries to collect the best of both worlds. One is pre-training the vision backbone. The other one is zero-shot adaptation to any unseen tasks without the per task human adaptation. The idea is very simple. It takes a pre-trained image encoder, and this image encoder can generate the embeddings for image input. And then with a given image and text pairs dataset, it tries to only tune the text encoder. So it's quite lightweighted comparing to contrastive from scratch pre-training. It tries to map the text encoder, the embeddings, as close as possible to the paired image embeddings. So after this tuning process, the image and text embeddings would get closer and they can perform contrastive learning on new problems. And this is a comparison of locked image tuning versus fine tuning. With locked image tuning, it does not need any per task adaptation. It can be used to any new tasks with text prompting. Just write down your classes, then you get your answer. This is an overview of all of the three methods I just mentioned. On the top row, it's fine tuning. You can pre-train the model on big data set and then fine tune on each task and get a very good quality on different downstream tasks. And with contrastive learning, it tries to learn this image text model from scratch. And then for image, like it can write prompts like a picture of a pink primrose, or a picture of pocket orchid, or a picture of corn poppy. And then the model can rank those and get your target class. And with LIT, it takes pre-trained model and only tune the text encoder. You can get the same property. And let's go back to this VTAB process again. And with LIT tuning, you just need to write down what you want without adaptation at all. This slide summarizes a high-level idea. It's very simple. On the right most hand, it's standard clip and align method, which tries to train the image tower and train text tower from scratch. And with LIT, we simply lock the image tower, and that's it. And we take it from a pre-trained weight. Of course, there's something in between. It's like also take the pre-trained image model, but we fine-tune this model on the image text data sets. This has led to new data efficient state-of-the-art results. On the left-hand side, we compare the from scratch method clip as well as our reproduction. And with LIT setup, like it gets a significant boost on the downstream metrics. We also tried the method in between, which is fine-tuned the vision backbone. It also pre-trained, but we fine-tuned on image and text. You see this falls in between. And on the right-hand side, it's on the private dataset, also with clip align. They're also on the in-house dataset. Those methods get slightly above 76%, which is roughly the same level as Resident 50. And with LIT, we actually push this higher than 85% zero shot on ImageNet. This table shows more state-of-the-art results on both private and public datasets. On ImageNet, you see the similar numbers as shown in the plot. And what's very exciting in this table is that we show the results on public dataset. And this has almost double the numbers before this paper, which is on clip 31%. And on the open clip reproduction is 35%. And with LIT, we can actually make this almost matching Resident 50. And on a few other out of distribution datasets, the LIT model also gets quite promising results, as well as a zero-shot transfer on VTAB natural subsets consisting of 7 tasks. The LIT model also matches the from scratch method like Resident 50, which has seen already downstream per task training examples. Next, I will explain why this could work. This slide compares web data versus human-created dataset. Like on the left-hand side, it's a label with all of the images human rated as that label. It's a snapshot from CIFAR 10. You see all of the 10 classes as well as a very high quality, less noisy dataset. But on the right-hand side, it's crawled from web, super large scale, billions of image and text pairs without human rating, just with very basic filters, like the image size, shape is not like a bar, or the text is not too meaningless like an image or JPEG. And you can see that there are some text captions. It's quite noisy still, like this on the middle, on the right-hand side. Some for version as of 21.57, 29 June 2010. It's likely some version control from some certain websites. And there's also some alt text like motorcycle front wheel. This is very high quality. So the hope is that from those high quality and sometimes noisy web data, if the scale is big enough, the data can actually speak for the model and learn good signals. This slide shows the design choices of the LIT setup. Like if you remember the 3 delotions, UU is purely from scratch, and LU is a locked image tower but unlocked text tower. You see that on ImageNet, from scratch is a worse setup, and LIT is the best. Fine-tuning the vision backbone falls between the 2 setups. And on the left-hand side, we shows even more design choices. Other than the LU, UU, and the small UU, we also showed using a pre-trained text tower. And also we tried locking the text tower as well instead of locking image tower. So you can see that on the second letter, it shows the setup of the text tower. Unfortunately, in our setup, using a from scratch text tower, the small u, or using a pre-trained text tower does not bring us too much difference. And using a locked text tower just makes the model very bad on those benchmarks. Yeah, we leave this for our future work to make sure whether we can also making the advantages of pre-trained text tower. And on retrieval tasks like image text retrieval or text to image retrieval, it's also interesting that we see the gap between locked image tower and unlocked image tower becomes much, much smaller. And also in some case, the unlocked image tower, which means we fine-tune the model on image text data, actually can give us much better performance, like here on text to image retrieval. So the conclusion of whether to lock image tower or not lock image tower, it's purely depending on the downstream task, and it's not always good. And this plot shows the training loss of the 3 setups. And you can see that the best training loss is achieved with this green curve. And the green curve is actually fine-tuning the image tower, and text tower is unlocked. With the locked image tower, the training loss is the worst. It's a blue curve. And you can see that the trend has changed. If we look at the loss on different downstream datasets, like on ImageNet dataset, the training loss of LU actually goes to the best one, and the unlocked one is the worst. So this is consistent with observation on the 10-shot classification. On the bottom row, you see that with ImageNet transfer with linear 10-shot, the locked image tower is of course flat because the vision tower has not been adapted in this process. But if we take the same pre-trained backbone, but we unlock this during the image text fine-tuning, the quality of the vision backbone actually gets destroyed. You see the 10-shot goes from 70%, quickly go to 40%. And then by training longer on the image and text dataset, it's slowly recovering, but still far from the locked setup. So this explains why the locked image tower works so good for ImageNet classification. And for the from scratch method, it's slowly going up from 0 until the end, which falls still behind both LU and UU. Is it due to the labels in pre-training? Because for like even on JFT pre-training or on the ImageNet 21K pre-training, the model has already seen the labels. So we did this ablation test of pre-train a few vision models with labels or not with labels. And all of those models got similar performance on ImageNet. If we look at the upstream numbers, like they all fall into between 75 and 80%. But we try to apply lead tuning of those models with self-supervised loss or with supervised loss to downstream tasks. And it's very clear that for the first 3 rows, they all achieve similar ballpark, like 55 0-shot. And those actually covers does not use labels and use labels. And for the bottom 2 rows, it shows the numbers which is far from the average range, like a super high 64, because it has already seen the original ImageNet dataset with labels, so it doesn't make sense for 0-shot numbers there. And also on places, it's a much different dataset on scenes instead of objects. And you also see the numbers on downstream transfer, it goes quickly to 28%. So this means that as long as your model can produce high quality embeddings, that means the model can likely transfer well to your downstream task in this lead tuning setup. This shows the impact of duplicates, because with web dataset, the biggest concern is that your downstream datasets is actually also crawled from web, and the image and the text may be leaked to your pre-training dataset. So to verify this point, we also did a very strict test. We try to report the original numbers without any dedupe, or we try to dedupe all of the test examples from the downstream dataset to the from our image text dataset to all of the downstream test splits, and we removed almost 2.6 million examples from the pre-training dataset. And this almost produced similar, almost consistent results without too much job. And we also did a very comprehensive cover of all of the downstream examples, not only the test split, but also training split plus test split. Like on ImageNet, we try to remove duplicates to the 1 million training examples and also to the 50K testing examples. This leads to even more duplicates from the upstream dataset. And this also does not lead to big drop on the quality, especially on image text retrieval and text to image retrieval. This leads to better quality. Finally, we also try to evaluate this model on different ViT architectures, like on mixer and on big transfer. All of the models achieves good quality. And the good signal is that the ViT actually produces the best performance comparing to other architectures. One of the hypotheses is that the text tower is also vision transformer, and the ViT as vision backbone brings the representation closer for vision for the 2 words. This plot shows the impact of the scale for both image tower and for text tower. So from the x-axis, you see that going from the smaller image tower to the bigger image tower, one observes a big jump, especially on the smaller scale. And going to the larger scale side is actually getting saturating performance. And on the y-axis, the stacking bars shows the quality on the text tower, like going from base to large to huge. And you can see that we're using a base text tower is probably enough. And increasing base to large give us a big jump, and increasing from large to huge does not get too much boost. This is result shows the impact of batch size in contrastive loss, because in the mini batch, all of the elective examples are considered as important there, because it tries to learn the embeddings, making your positive pairs close, and the gap between positive and negative pairs far away from the positive pairs. So the more negative examples, the more likelihood you will see hard negatives, and making your model more robust. And it's quite clear that using very small global batch size leads to low quality, and going from 2K to 32K, we show very we see very significant boost, and this trend actually does not converge. This also hints more hegemony using even larger batch sizes. Here we also try to adapt this zero-shot model on very diverse tasks on VTAB, with 19 different tasks covering natural, like plants, or the different shadows, and the specialized tasks like the medical images or remote sensing images, and the structured tasks in the reinforcement learning environment, like predict the distance to the next reward, and the clever data sets with different shapes and different numbers counting how many of the objects are there. So on the left-hand side, you see the performance of the zero-shot model on those different downstream tasks. It's quite interesting that the natural task, the bottom line is random guessing, and the top line is supervised REST-50 model. So with zero-shot models, by a big sweep, we can actually match the supervised REST-50 performance. This gets so much better than the random baseline. But however, if we go to specialized, it's already a different domain compared to natural images. This already gives us a huge job. And then going to rightmost, showing the performance of this model on structured data set, it's almost not much better than random guess. We also try to engineering on a prompt on how to write a good text prompt for the structured tasks, like the distance. The original data set just shows the integer number as a distance, but in our case, we try to write it's close, it's far, and also write in different formats. It doesn't help too much. So this leaves a lot of hegemony for the future tasks, how to use those zero-shot transfer to unseen downstream tasks like robotic control. The model also can do multilingual tasks thanks to a locked image tower. It's just like a multilingual kit. It learns to speak from parents from different countries, and the kit may already link the different languages without people teaching them how to translate. And we hope this could also become an emerging property of LIT, because of the image tower is frozen. So the text tower try to embed a different language text and try to map to the same anchor point from the image tower, and this may give us the multilingual probability. This plot shows it's indeed the case. If we train the model on the original clip subset, which is a filter subset by the clip paper, only contains English, the model actually performs pretty good on English dataset. But if you look at other translated ImageNet variants, the model just drops by a big margin. But if we expand this subset to the full IATM version of clip, we see a very small jump on English. But on other languages, like on French, on German, there's a huge jump across the board. And we test this on the Wikipedia image and text retrieval datasets as well. There's a very significant boost by using LIT and on the multilingual dataset. Okay, next I will quickly show some demo of this model. So in this case, the model can recognize the red Honda Civic, the specific car type, and the car color, as well as two towers in the background. And here, a blue car parking in front of green and pink walls. The image of 7 cats. So the model shows some probability, shows some capability to count the images. But however, if we add some change the prompts or making the image slightly different, this may simply fail. And in the bottom, a cow sleeping on the beach is quite an exciting example, as the common belief is that if the model is trained on a large-scale data set, maybe the model cannot generalize to all the distribution cases. Like here, you may recognize a cow based on the background, like grass, sleeping on the grass. But actually, it's no. With the web data, the model has seen big enough, and it's capable to do those outer distribution cases. And here shows some multilingual examples, like Chinese New Year celebration. It ranks Chinese text as at the top. And here, Thai Water Festival. This also recognizes original Thai words, ranked not at top, but top 3. Of course, the model also have a lot of failures, like it cannot distinguish very fine-grained details from the image. It confuses grinning face with yawning face. And here's some live example. You can also play with it yourself. The most interesting thing in this case is that with pre-training on web data, we have observed that the model has shown some emerging capability of doing OCR. Like in this case, it tried to rank the text prompt with iPod high. A sticker with text iPod is actually already as high as Apple. Apple with a sticker with a text iPod is a top one. So next, I will introduce some alternative way of the standard 2-tower contrastive learning with a mixture of experts. The idea is very simple. It tries to use a single shared ViT model will replace every other MLP with MOE of MOE of MLPs. And in this case, it tries to take text as input, image as input, and each modality uses the modality-specific embedders to produce embeddings for different tokens. But after this, the 2 types of tokens are processed simultaneously by the LIMoE architecture. And the router, which takes different tokens and try to send them to different MLP models, it's actually agnostic to the type of tokens. It can process image token and text token. It does not know what type of token it's routing. And in this case, we also use 1 expert per token to make sure this can match the dense model in terms of flops. It does not take advantage of more parameters. And any expert in this layer can process any token. There's no predefined modality-specific experts. So it's just a unified model can process in different modalities. And we observe the natural emergence of unimodal and multimodal experts. So sometimes a model is taking a lot of tokens from image modality thanks to this router. And also some model can take care of both image and text modalities. So this method also achieves a close to state-of-the-art performance. So just in this table, we highlight the 2 methods using standard 2-tower contrastive learning setups and achieving good performance on ImageNet 0-shot. And with LIMoE, we use a much smaller backbone, like only H14 in this case, because it's shared across image and text. So there's only one setup for both towers. And this model shows pretty good performance, 84.1 on ImageNet, given much fewer compute. And finally, I will quickly mention continuous scaling up the vision backbone from ViT-G to ViT-E for vision and language downstream tasks. Just a bit background. So this scaling laws shows that the Pareto frontier that by continuous scaling up the compute, the model may saturating on ImageNet fine-tuning error rate. In this case, it's 0.09 according to the estimation. And if we look at the papers with code benchmark, we are getting pretty close to that limit on ImageNet. And on the other hand, we also try to re-evaluate the ImageNet validation set. For example, we observed a lot of issues with the ImageNet ground truth. Sometimes there's multiple valid answers on the top right corner. You see this image, the old label says it's ant, but our human rater says it's ant and ladybug. And the second point is there could be some play mistake, or it needs a lot of context to understand, which is hard to do just from the model perspective. For example, in this case, it shows purse and the wallet. Both are actually valid answer for this image. And then passenger car, school bus. Yeah, it should be school bus. The old label is wrong. It says it's passenger car. But if we look up the Google search, passenger car is also like those trains taking a lot of passengers. And the third kind is unresolvable distinctions like laptop, notebook, or sunglasses. So all of those indicate that we do not want to make ImageNet model 100% because it's simply overfitting to wrong labels. But nevertheless, we continue to try to scaling up the vision backbone from ViT-G to ViT-E and see what's going to happen in this case. The biggest difference is this model is almost double the parameters from ViT-G, which is 1.8 billion to now 3.9 billion parameters. And we have observed very marginal improvements on vision-only tasks, like on image 10 shot and image 25 shot. This model only gets less than 0.5% boost compared to the past ViT-G, because we know this is the case as the model is saturating on those vision tasks. What makes us super exciting is that we try to expand the scope to vision language dataset, vision language downstream tasks by plugging this vision backbone with the encoder and decoder language standard T5 language model on top, and the model can actually decode the text prompt, text answer. So this model can be used for COCO captioning or can be used for VQA tasks with a vision language input and try to output the answer. We have observed a very significant gain compared to the ViT-G counterpart. With a ViT-G baseline, like on COCO, this model gets close to 3% boost. And on VQA V2, this model also gets to more than 2% boost. And the reminder that this model, ViT-E, it adds only 13 more parameters to PaLI over ViT-G, which used in total 17 billion parameters. So with such a small increasement on the vision parameters, leads to such a huge gain, makes us hints more headroom for the future scaling of vision backbones. Okay, I will conclude here. And a quick summary. In my talk, I covered the locked image tuning, which provides an alternative to fine-tuning to read out frozen embeddings from any pre-trained vision backbone. And then the language and image MOE, it can handle contrastive learning, but with a single shared backbone using a model agnostic router, and still achieves good performance on downstream tasks. And finally, we continue scaling up the vision transformers, although this achieves saturating gains on vision tasks, but we see large improvements on vision and language downstream tasks. Thanks. And any questions?
Yes, thanks, Xiaohua. So let's have one question. So let me, in fact, ask one question. So you can see that this is both for Neo and for Xiaohua. You can see that we are trying to scale up, build this foundation model, very, very large foundation models. But in many cases, we could kind of, when we really use the models, for example, on our PC or even on AR glasses, on edge devices, this kind of big models cannot be used. So I want to get your opinion of how to better use of vision foundation models.
Yeah, so I think there are two cases. So the first case is what are the part needs real-time calculation? So for example, with LIT, like for large scale system, we can actually use very large vision backbone to extract the embeddings, actually pre-compute the vision embeddings. And that's it. This can be stored with zero cost, even though user want to query something like Google Photos. They can calculate all of those embeddings from a super large vision backbone. But we use a very small text tower, like a tiny text tower. This can extract text prompts for user real-time input. And this can be extremely fast, but also getting benefits, advantages of large vision pre-trained backbone. So that's the answer of going with the alternative rule of making advantages with pre-compute, but still does not block use cases. And the second case is if we really want on-device model, can do those vision representation extraction and doing detection segmentation. then I think distillation could be one possible ways. We also have work on that direction in the past on image classification distillation. I did not cover it in my talk. And we are also actively working on detection segmentation to make sure we can actually serve the small models. Yeah, if you want to add anything, feel free.
I think you covered the main two ones, yeah, like pre-computation, distillation. I'd also add maybe pruning is something that's starting to work better and better. I guess model pruning is something that's been more in the academic sphere up until recently, but we're starting to see with transformers, pretty impressive results start to come out from the pruning literature. Especially if it's unstructured pruning or one's using sort of CPUs also. So I think that's something also to look to for the future.
Yeah, this reminds me of a fourth use case. It's like, thanks to transformer, the sequence length is very sensitive to the final flops. So for example, the on device can still use a large model with lots of parameters, but use a super short sequence, like with 8x8 patches and with ViT large. Maybe this is fast enough comparing to a ViT base, but with 32x32 patches.
Yeah, okay, thanks. I think this is an important topic for researchers who are working on foundation models to think about, because finally we want to serve kind of real world models. Some models should be very, very small, like models on AR glasses. It's quite difficult to really serve with foundation models on those kind of devices. But anyway, so let's leave the discussion kind of later.